Design of reinforced concrete rectangular beams. Sample problem. Determine the width, depth, and the quantity of steel bars for the beam to satisfy the criteria below. We are given here some of the parameters to be used. We have design steel ratio 0.012. We have the design moment or the ultimate moment or the maximum moment that the beam will carry, that is 300 kip-foot. Then FC prime is 4,000 psi. This is the strength of concrete. Fy is 60,000 psi. This is the yield strength of steel. And the rebar size is number 9 rebar. Here's the solution. The first thing to do is assume that the beam is in tension or tension controlled and solve for BD squared using equation 3.4. So we are to solve for the BD squared using the equation below. Okay, let's check if we can solve this equation using the given parameters. Mu is given. Here we have Mu. Then steel ratio design is also given. So we will check. Fy is of course given. Here given. Then FC prime is also given. Then since we are assuming that the beam is tension controlled, phi is equal to 0.9. So this is also good as given. The only thing lacking here is the BD squared. So we have to solve for BD squared. So manipulating the equation, transposing, or using shift solve, because this is only one equation, one unknown, we can solve for the value of BD squared. We take the BD squared as one variable, by the way. So we have already the required BD squared. And the next thing to do is to try beam sections that would satisfy the requirements of BD squared. Okay? So first, we start with 12 inches. This is the most common beam. So let's try a beam that is 12 inches. But we don't know the depth. Okay? So let's have a trial and error here. First, we try, let's say, 16. Okay? Obviously, if you multiply 12 times 16 squared, this is the answer, and this is obviously smaller than 6,213. So there is a comment here. Select another width or depth. Okay? Because the BD squared does not satisfy the requirement. Okay? You can also look up here if you want to program a formula that will somehow produce this kind of comment. Okay, so let's have another value, 17, 18, still not moving, 19, 20, then 21, 22, 23. Okay, so if we plug in 23, the section is now satisfactory because 12 times 23 squared is equal to 6348, which is this, and this 6348 is greater than 6213.45. Okay, so therefore it's more than the requirement, but not too much. Okay, if you go for 24, it's satisfactory, but it's not economical. Okay, if you go even, you can even go higher. If you want 30, it will be way higher. The BD squared will be way higher than the 6.2. But then again, it will not be economical. So the most economical is 23 inches. Can you go 22.5 or 22.6 or maybe 22.8? Still not 22.8. it may be satisfactory, but it's not practical, okay? Because when we specify dimensions for beam, it should be in whole number, okay? So that the fabricators of the formworks will have it easier to fabricate the beam, okay, or the formworks of the beam. So we go for 23 inches. Okay? So after that, we now declare the final beam section. So hence we declare this 12 and 23. This is now our final beam section. And of course, we have to specify our H, okay, because your beam looks like this. This one is the steel bar, or the location of the steel, and this is your D, and this is your H. Okay, and H is normally 3 inches. Okay, the covering is normally 3 inches. It could go higher or lower, but for simplicity of calculation, we peg it at 3 inches. Okay, because in the code, the required covering is 1 and 1/2 inch. That is your covering. So, covering plus the size of the stirrup plus half of the rebar diameter, that will be approximately 3 inches. And for simplicity of calculation, we just add 3 inches here. Okay? So, we have declared the final section. Now, we have to calculate for the required steel area. Okay? And the required steel area is having this formula, rho BD. Okay? Because it's coming from the steel ratio, that is area of concrete, area of steel over area of concrete. So AS over BD. Okay? So manipulating that, we can have AS is equal to rho BD. Okay? So we are given the steel ratio design, and we have already finalized B and finalized also D. So we can have this one. This is in square inches, 3.312. Now, after declaring and having the required steel area, the next step is to try also and declare the steel quantity that would satisfy the required steel area. Okay? So, in the problem, we are given the size to be used. This is number 9. Okay? So, here in this yellow cells, this is our trial and error area. So, the rebar diameter is number 9. If not given, if the rebar diameter is not given, you can also have a trial and error for your rebar size. Okay, combination of the quantity as well as the diameter would give you the best and most economical rebar combination. Okay, but since we are given the bar diameter, then we don't have to edit this one. This is number 9, and we can even link this one up to this cell. Okay, we can link this one to this cell here. And for the number of pieces, we have to make sure that the total steel area here is greater than the required steel area. Okay, it should be greater than. Okay, and I have a comment here. If it's less than, then it will say that the number of bars, increase the number of bars. Let's say you start with number 2 or 2 pieces. So it will say provide additional bars because the total steel area is less than the required steel area. Let's say if I have 3, this is still lacking. 2.98 is less than 3.312. And if I go for 4 pieces, then it will now be satisfactory. Okay, so this is already checked. The next thing to do is to check the beam width, if the rebars will fit inside your beam section. Okay, so if you try to recall, this is how a beam is being laid out. You have here the stirrups, and you have the main bars, 4 pieces. Pardon for the drawing. Alright, this one is, it should be 1.5 inches. And this one, if not given, use number 3, or in metric you have 10 mm. So this one is 3/8 or number 3. The stirrup is number 3. And then this one, this should be 1 inch. Okay, from face to face of the rebar, that should be 1 inch. So you have to fit all of the rebars. Okay, so in order to fit that, you have to sum up the required beam width. Okay, so to sum that up, you have the covering, which is 1.5 inch, then times 2. Okay, because there are 2 faces here. Then the stirrups, that will be 3/8, so plus 3/8 times 2. Okay, then plus the number of bars, plus n times diameter of rebar. Okay, diameter of your selected rebar, then plus this one, the space between the rebars. It's always 1 less than the quantity. Okay, we have 4 rebars, so the space is 1, 2, 3. So that will be n minus 1 times 1 inch. Okay, because that is the standard spacing in between rebars. So adding all those up, you can have 11 and 1/4 inch. And 11 and 1/4 inch is less than the specified or the final width that you have set, which is 12 inches. That is less than 12 inches. So therefore, the beam width is okay. Otherwise, you have to increase the width, or maybe look for another rebar, maybe a higher diameter rebar that would satisfy the spacing. Okay, because if the rebars are too close, then the aggregates cannot anymore pass through, and it will cause honeycomb and all sorts of defects in the concrete. Alright, so it needs to satisfy the total steel area, and also it needs to satisfy the total beam width. Okay, if you go for 5, let's say for the sake of example, if you go for 5 pieces, the total required beam width will already be 13 and 3/8 inches. And that is higher than 12 inches. So it will say increase the beam width. Okay, although this one is satisfied, but the other parameter, which is the beam width, is not satisfied. So either increase or decrease. So we decrease to number 4, but this one is already satisfied the total steel area. If we go for number 3, the beam width is satisfied, but the steel area required is not. So 4 is really the magic number here. Okay, so practically we have solved the problem. We have answered the width and the depth, and we have already answered also the number of rebars required. Okay, so in some problems that is enough. But if you want to have a full review of your design, you need to check for the steel ratio. Okay, so check this one in terms of code requirements. So calculate the actual steel ratio based on the 4 pieces of number 9 and use this formula. Rho actual is AS actual over BD. Okay, so AS actual, which is this, over BD, and your BD will be your final section, 12 by 23. So you have this actual steel ratio. Then compute for the minimum. In computing this one, check my other video to compute for the minimum steel ratio as well as to compute for the maximum. Okay? So compare the minimum, maximum, and the actual. And the actual, rho actual, should be less than or equal to rho minimum, and it should be less than or equal to rho maximum. Okay? So our rho minimum is 0.0033 and our maximum is 0.018 and our actual is 0.014, so it is within limits. Okay? This one is satisfied. Then we check for the capacity of the section. Depth of compression stress block. You can see my other video for this also until you get the ultimate moment capacity. Okay? And this one, it should be compared. It should be greater than or equal to mu. Okay? And our mu is 300. So this one is satisfied. Alright? Thank you very much.